Hi, my name is Mark Rosen, and it's my pleasure to deliver this keynote presentation for the first World Sustainability Forum. The title of my talk is Energy Sustainability for Buildings and Communities. A little bit about me first. I'm Editor-in-Chief of the journal Sustainability, which is a key sponsor for the forum. Also, I'm a Professor of Engineering at the University of Ontario Institute of Technology in Canada. The outline of my talk, which also describes the motivation for it, is shown here on a background of the skyline of the city of Toronto. First, the most important part of this talk is a focus on sustainability in general. Secondly, I focus in on sustainable energy use and its particular role in the bigger picture of sustainability. And thirdly, I'm going to look at buildings and communities and how sustainable energy use can interact with them and help them perform better. Starting with sustainability, I want to talk about what it might mean. There are many interpretations of sustainability. One of the most common is to look at it as three intersecting circles where you have independent factors that are environmental, social, and economic. Within those, if you achieve simultaneously environmental sustainability, social sustainability, and economic sustainability, you end up in the center here, where you have what would be viewed as sustainability or sustainable development. If you achieve only two of these, like environmental and social sustainability, you might have a bearable society, but you would not necessarily have an economically thriving one. Similarly, if you have social and economic sustainability together, you might have an equitable society, but you would not necessarily have a pristine or protected environment. Only when you achieve social, environmental, and economic sustainability together do we have true sustainability. It's a very multidisciplinary field. The journal Sustainability, in my role as editor, has taught me a lot about sustainability and how broad it is and how differently interpreted it is by different communities. The journal itself is international and open access, allowing readers from all over the world, as long as they can get on a computer, to get access to the papers. But the papers that have come in the technical domain, science and engineering, or the environmental domain, or the social, political, economic domains have shown me the true breadth of the field. It is important as a field as well. Sustainability is critical. I am past president of the Engineering Institute of Canada, an organization in my country that's over 100 years old, and we recently went through a visioning exercise, and our short vision is Engineering for a Prosperous, Safe, and Sustainable Canada. The emphasis is mine there, but I wanted to point out how sustainability took a lead role in the vision for the Engineering Institute. This institute is a broad umbrella organization which has members that are the engineering societies in Canada, like the Canadian Society for Mechanical Engineering, Canadian Society for Chemical Engineering, and on and on. The presidents of those organizations sit on the board of the Engineering Institute of Canada, allowing us to talk about cross-disciplinary issues. Sustainability is one of those. Now I'd like to hone in on energy sustainability. But first I have to ask, what is energy sustainability? That was not easy for me to determine. I went to the dictionaries, could not find a clean definition, so I had to make one up myself. And this is what I came up with: the provision of energy services in a sustainable manner. And I was very happy with that until I spoke to linguists who told me that you cannot necessarily use the word you're defining, sustainable, in the definition of energy sustainability. So I had to amplify. What I mean is, energy services are available that are sufficient for the necessities of all people throughout the world, now and in the future, that are affordable and therefore attainable by them, that are environmentally benign and therefore not damaging irreparably our environment, and lastly, that are acceptable to the people and the communities that will adopt different energy measures. And that's a very important one. For example, I would propose try putting a nuclear power plant into a community that's anti-nuclear, and you might spend 10 or 20 years trying before you finally throw in the towel and give up. Whereas if you pick a community like the one in which my university is situated in Oshawa, where we already have about 12 nuclear reactors and a fairly acceptable community that sees benefits of nuclear power, you'll have a much easier time.
Sorry.
What are the requirements of energy sustainability? From my engineering perspective, I come up with 4 main ones plus a 5th one that goes beyond the engineering domain. The first is that we use sustainable energy sources, and they might include biomass. Here we have palm oil trees from Malaysia, nuclear power perhaps, which does not emit CO2 or other greenhouse gases during its operation, solar energy, and others. Now, each of these is contentious. No one says that they are purely sustainable, but certainly they avoid many of the pitfalls of fossil fuel combustion, the limitations that we have in resources, the emissions that they cause. Also, wind power would fit into the sustainable envelope. Here's a picture of a device, a vertical axis wind turbine that we've done research on at my university. It could work into an urban community as shown in the bottom right with the old City Hall in Toronto in the background. And in the upper right we have pressure distribution curves where we're analyzing the technical behavior and efficiency of the device, trying to improve it. The second requirement for energy sustainability is that we adopt appropriate energy carriers. Now, sometimes an energy source is a carrier, like oil. Other times the carrier is something we produce because it's convenient, like electricity in the bottom right, or perhaps hydrogen, which is shown representatively in the bottom right by a hydrogen fuel cell vehicle. There are many secondary energy carriers shown here: work electricity, thermal energy, be it hot or cold, fossil fuels, secondary chemical fuels, and in that category there are many, as shown in white, including at the bottom hydrogen. The hydrogen economy has received a lot of attention recently, so I'd like to amplify on it a little bit. What we have is a hydrogen economy based on a very simple concept that we can ultimately use renewable energy sources at the bottom here to achieve at the top useful energy services or useful energy products. To do that, we have a closed cycle in which we produce hydrogen typically by taking water from the environment and splitting it to hydrogen, which we will use, oxygen, which we can either use as a byproduct or return to the environment. The hydrogen can be transported and stored before it is ultimately used to produce that useful end product or service. The resultant of oxidizing hydrogen is water. We take oxygen in to do that. That oxygen can come from the environment where we put the oxygen from splitting water, and the water returns to the environment to be used again. The benefits of the hydrogen economy are that we have an energy carrier, chemical in nature, that complements electricity, our non-chemical energy carrier, and together those two carriers allow us to satisfy many of the needs of society from an energy perspective. The third requirement of energy sustainability is increased efficiency. If we can do more with less, we can stretch the reserves that. And by efficiency, I don't just mean simple efficiency of a device, but rather, yes, device efficiencies, but also system efficiencies, better energy management, where you try to control the energy flows in a system so as to achieve higher efficiency and maybe reduce demands instead of increasing supplies. Also, better matching of supply and end use, that is, if all you need is warming a house at 20 degrees centigrade, perhaps you can find waste heat from industry at 50 degrees centigrade to do that instead of burning natural gas at several hundred degrees to achieve that same use. Also, better integration helps with efficiency, and that might be designing, say, a city to allow transport hubs to be energy efficient, to minimize distances that people travel, to keep industry together where wastes from one industry on an energy sense can become inputs to another. Finally, design of systems for using energy more efficiently. or being more energy efficient overall is part of efficiency from my perspective. Exergy analysis is an advanced tool based on thermodynamics, particularly the second law of thermodynamics, that allows us to assess and improve efficiency. Exergy is a measure of energy quality, something we often neglect when we deal with energy quantities only. It's a non-conserved quantity. Energy quality is degraded every time we do something with energy, whereas energy quantity is actually conserved. And exergy analysis allows us to determine meaningful efficiencies. That is, efficiencies that always tell us how nearly we approach true ideality or physical perfection. Energy efficiencies don't always do that. Exergy analysis helps identify the real losses that detract from perfect efficiency, and by doing that, it identifies for us the improvement potential, the true improvement potential of energy system. So it's a very useful tool. But let me try to illustrate how it might work. As a system, let's consider not just an engineering device, but the whole planet. The planet is basically in balance. We have solar energy from the sun coming in at the upper left to the Earth, which is a high exergy form of energy, high quality. Going out at the bottom right is thermal energy, in quantity equal to the solar energy coming in. But that carries low exergy because it's at a lower temperature than the energy coming in from the sun. The net result on an energy perspective is that the Earth gains as much energy as it loses. So it's hard to imagine what its efficiency is. Whereas the exergy efficiency does tell us something. We have high exergy coming into the Earth. That is what drives photosynthesis, cycles in the atmosphere, in the waters, life development and organizational patterns as we see them. And the waste, the low exergy that leaves, is something that we have to get rid of because of inefficiency of the planetary processes. So exergy is used in driving the processes on Earth. Energy analysis doesn't tell us much about this picture. You can substitute for the Earth any device and you get a much better, clearer picture of its performance and efficiency using exergy analysis. Now exergy is nothing new. There is increasing recognition. I co-authored a book several years ago on exergy with my colleague Dr. Ibrahim Dinser, and we together started a journal, the International Journal of Exergy, almost a decade ago, and it's thriving with lots of papers about applications as well as methodologies in exergy analysis. The fourth requirement for energy sustainability is to reduce environmental impact. And whether, as shown in the bottom center here, that is taking care of global warming, addressing it so that climate change does not proceed as many predict it will, or using advanced tools like life cycle analysis, in which you look not just at the operation phase of a device, but at its full cradle-to-grave life, from the production of the device to the use of it to the ultimate disposal or recycling of it. As well, environmental impact can be reduced with techniques like carbon capture and sequestration, in which we, instead of releasing carbon dioxide to the atmosphere, we capture it and try to store it somewhere, avoiding greenhouse gas emissions. Finally, the fifth aspect of sustainability is somewhat of a catch-all, and that is to satisfy all other aspects or facets of sustainability, and those including, as I've shown here, attitudes that people have towards sustainability, laws to support sustainability, education so people are aware of what sustainability means, what needs to be done, lifestyle adjustments where necessary to achieve sustainability, what the impact is on living standards, on health, cultural development in the context of sustainability, policies to support it, ethical questions that arise, and urbanization issues all relate to sustainability. Now in the third part of my talk, I'd like to address specifically energy sustainability for buildings and communities. But before I do that, I want to talk about energy storage, which is some ways a hidden need for energy sustainability in buildings and communities. I've shown here an underground thermal energy storage tank, which is about 5 meters across, 3 meters deep, stores water that's collected using solar energy all summer long for use to heat a building all winter long. As I've illustrated there for solar energy, storage is very important to being able to use intermittent energy sources, as many renewable energy forms like solar and wind are. I won't go through energy storage in detail, but I put this here to point out that there are many benefits listed on the left of this slide to energy storage, beyond just facilitating renewable energy sources. As well, there are many technologies that allow us to store energy, some of which are commonplace like batteries. Others are more in development in hopes of providing more efficient energy storage in the future. All will help towards energy sustainability. Now, looking at building communities, the first thing I'd like to focus on is energy-focused building design, a critical component of sustainable energy use in buildings and communities. This is my university, University of Ontario Institute of Technology in Oshawa, Ontario, Canada. Beyond the buildings, you see the green quadrangle there, and underneath that is a borehole thermal energy storage system hooked up to a ground source heat pump system that's used for heating and cooling these buildings year-round. In fact, for heating and cooling most of the campus. Here's a schematic of it. We have here the buildings that you just saw in the last diagram, and this is the green quadrangle. Here's the library and the engineering building. And there are more buildings not shown. Underneath that quadrangle are 400 wells going down 200 meters each into the ground, separated by about 4.5 meters. Warm fluids go down into the wells, heat leaves the tube, goes into the surrounding soil and rock, heats it up, and is stored there for use later on. Similarly, cooler fluids can be put into the wells, stored in the rock and soil mass, and the coolness can be extracted for use in air conditioning buildings at a later time. So this is UOIT, University of Ontario Institute of Technology, borehole thermal energy storage system hooked up to a ground source heat pump, GSHP, that facilitates the workings of the storage system. Looking at 4 of those 400 tubes in detail, we have fluid coming from the buildings or the heat pumps going out to a tube through a header going down 200 meters, back up, and returning to the system in 400 different tubes. The ground in which these are located has about beige section here, about 40 meters depth of overburden. Then we turn to rock. We have about 20 meters of shale, and the next 140 meters is limestone rock in the ground. The economics of the borehole thermal energy storage system at my university are quite impressive. We have direct savings of about 40% on heating costs and 16% on cooling costs. Other indirect savings also accrue. We didn't need to pay for a boiler plant, and we don't pay for the associated potable water and chemical treatment that requires, and we don't pay for the rooftop cooling towers and the structural supports in the buildings that are needed to accommodate them. As a result, the payback period for the system is about 5.5 years. The high-efficiency HVAC equipment has a payback that's quicker, about 3 to 5 years. The borehole well field with the 400 holes is about 7.5 years payback. The main challenge is that although you save money over time, you have to pay the money up front. There's a larger initial cost, and that dissuades a lot of people from putting in such sustainable energy systems. Another aspect of sustainable energy buildings is net zero energy buildings. One is shown here that is based very much on solar energy as a primary input. Here you have photovoltaics on the roof producing electricity and solar thermal collectors producing heat for heating the building. You also have passive solar design where you have windows that allow sunlight in when you want to warm the building and have blinds that would shut and stop that sunlight during periods when you don't want to be heated. There's active and passive thermal storage in there, a heat pump system that's heating and cooling the building in conjunction with the ground energy system. The electricity from the photovoltaics can run lights and appliances, as well be sold to the grid. As well, it can charge transportation vehicles like a hybrid electric vehicle that runs partly on electricity. The net result of this type of building is that it uses as much energy as it produces, making it a net zero energy user over the entire year. In Canada, we've begun a major research initiative in support of net zero energy buildings. We've created the NSERC Smart Net Zero Energy Buildings Strategic Research Network, which links about 15 universities and almost 30 professors. The project just started. It's about $10 million all told over 5 years, and it has 5 main themes as shown here: integrated solar and HVAC systems for buildings, active building envelope systems and passive solar technologies, mid to long-term thermal storage for buildings and communities, smart building operating strategies, and finally technology transfer, design tools, and input to national policy. All of this research is aimed at making smart net zero energy buildings a reality in a large way in Canada over the next 10 or 20 years. On the community side, here's a diagram of a community integrated energy system. This is the Drake Landing Solar Community located south of Calgary in Alberta, Canada. In this system, we have solar collectors located on garage rooftops for 50 or so houses that are in this community, the larger community having about 300 homes. Heat from those collectors, thermal collectors, goes into a short-term energy storage system, hot water tanks, and is then put into the ground with a borehole thermal energy storage system. When the heat is needed for the homes, it's sent through a district energy grid to each home, and colder fluid returns to pick up more heat from the storage or the collectors. Each home has a small solar collector on it used for domestic hot water heating. Here's a photograph of the system. You can see the Rocky Mountains in Canada in the background. These are the garages with their solar thermal collectors for heating, space heating, and these are the homes with their small hot water solar collectors. These 52 homes have managed to achieve a 90% solar fraction. That is, 90% of their energy needs are met through solar energy. Going to the broadest phase, we can look at sustainable energy cities, and here's a schematic that tries to convey the idea of cities that are designed so that energy production is from renewable sources like solar and wind off in the background, producing electricity and maybe chemical commodities like hydrogen that can be used in the city. The hydrogen might go into hydrogen fueling stations for transport vehicles. The electricity would help run our cities, lighting, appliances. There may be electrical vehicles like buses as well, and all told we end up with very clean cities that are sustainable. The energy services are provided at a distance from the city in clean ways. And that brings me to the end of my talk. As a closing, I want to emphasize that I think sustainability is truly essential, not just for an individual country like Canada, but for the entire planet. Energy sustainability is a critical quest in the overall seeking of sustainability. And finally, buildings and communities are a key part of that. In Canada, for instance, building energy use makes up about 30% of the national energy use. So getting sustainable energy use right in buildings and communities certainly goes a long way towards overall sustainability. And with that, I come to the end of my talk. I'd love to take questions if you have any. I thank you for taking the time to look at this presentation, and I hope you enjoy the first World Sustainability Forum. Thank you.